Hello, and welcome to the Albright Scholar for February 2023. My name is John Pankratz. I teach history at Albright, and each month it's my privilege to welcome BCTV viewers and residents of Greater Reading to take a glimpse inside our learning community up on North 13th Street, to look at the work being done by teachers and students, and to think a bit about its impact on all of us. Well, that's my lead-in every month. Think about its impact on all of us. And today we are going to talk about impact. We are going to talk about that thin layer of gases that surrounds all of us Earthlings with a wonderful expert on atmospheric chemistry, Dr. Laura McBride, a brand new professor of chemistry and biochemistry at Albright College. Laura, welcome.
Thank you, John, for having me here. I'm so happy to be here today.
It's great. It's great. You are a Pennsylvanian by origin. We can tell by your Eagles colors that you're wearing. Go Birds. Although I think the show is going to be broadcast after they've already won. Oh, can I say that? The Super Bowl. Just a prediction. But then, and you went to Moravian College.
Yes.
Was that a good experience?
It really was. Going to a liberal arts school definitely gave me opportunities I wouldn't have anywhere else, especially going to a really big school. I had that, individual attention with other faculty that we have here at Albright as well, and I got to do research and got to travel, and it was just some really good experiences that opened my eyes to kind of what I wanted to do, and that led me into deciding to go into graduate school to pursue a PhD.
Yeah, and there you went down to almost our nation's capital at the University of Maryland.
Yes.
Which is a great Research One university.
Yes, and I really enjoyed my time there. So it's right outside of DC in College Park. And it was a little bit of a change going from a smaller campus of, 1,500 students to 40,000 students. And so just kind of the size of the school was a little bit of, you could say, a culture shock. But I found that being in grad classes, it was just kind of being like back at Moravian, because those were smaller. You had the individual attention with the faculty, so there really wasn't much of a change.
It really is a team-based experience, isn't it?
Exactly. Yeah, and so working with your advisor, other grad students. And so I felt like Moravian had really prepared me for that, and that I was able to succeed and really do well and enjoy my time there, and that it was a really good experience.
Great. And as you applied to grad schools, I guess in some ways you at what point do you select your advisor and the team that you're going to be working with? Is that early on in the process?
Semi-early on, so it depends what school you're applying to.
Okay.
You normally have to have an advisor kind of identified, someone that you would want to work with. And then once you get accepted, you go down for a visit and try to determine, do you like the research that they do? Do you think you like them as a person, or the other students that are there? That
And vice versa, I imagine.
And vice versa, exactly. Yeah. And then you get, to make a decision of where you want to go.
Great, great. No, it's an exciting process. And you worked with one of America's great experts in atmospheric chemistry and atmospheric physics, I guess.
Yes.
And that's now your field as well.
It is, and I learned a lot under Ross Salowich at the University of Maryland, and I got a lot of opportunities to attend conferences as well as be a part of a lot of research, and so I think that's really helped me grow my knowledge and my skills.
Yeah. How early on did you know that an interest in the atmosphere, all these little gases that surround our globe, was going to be important for you to study?
I honestly didn't know until I got to grad school.
Okay.
Because I knew that I wanted to do something with the environment. And I kind of focused on climate change when I was at Moravian.
Okay.
And I actually had an opportunity to go to the meeting in Paris in 2015 when the Paris Agreement was negotiated. And that just really opened my eye, like, I want to be involved in this.
Yes.
And so when I was looking at places to apply for grad school, I was more focused on the climate aspect. And so my advisor, he did research in both atmospheric chemistry as well as climate. And so I came in to be on the climate part, and then once I was there, I started to get involved in the atmospheric chemistry. And so my first part of graduate school was climate science, and then my second half, you could think about, has been focusing on atmospheric chemistry and the ozone layer.
Great. Well, they of course go together
Yes,
in
they're very intertwined.
profound ways as well. I want to be sure to talk about this lovely article that you and Ross have out in Science Magazine. This came out late last year, right?
Yes, it came out on Thanksgiving, actually.
And it concerns the impact of the horrific wildfires that took place in Australia 4 or 5 years ago, and what they did to several layers of the atmosphere, right?
Yes. Yes, it was pretty interesting phenomenon. So just, what happened at the surface with the large fires and just the devastation they caused, but as well as the fires were so big that they created what we call pyrocumulonimbus clouds. So the fires created their own weather and their own clouds that rose about 20 to 35 kilometers into the atmosphere.
Okay, so
And
and that's up into the stratosphere, right?
That's the stratosphere.
I've checked out my
exactly.
levels here, and
Yes.
that's too high for a cloud to go.
Exactly. So for our viewers, clouds are normally in what we call the troposphere, which is where we live. And they don't make it into the stratosphere, except for very special situations like extreme convective thunderstorms can
Okay.
sometimes punch clouds into the stratosphere, but they only get a tiny bit into it.
Yeah.
They really don't go into the stratosphere. But these clouds from the fires got really, really high. And so it brought smoke and other chemicals from those fires into the stratosphere.
Was that from the heat of combustion that made them rise like
Exactly, yeah. The fires just were so intense that just the heat that it generated caused the air to rise that high into the atmosphere,
that? Wow.
which is not something you see every
No.
day. And so it was something that hasn't, as far as we know, happened before. And we started to see through satellite measurements as well as observations from the ground looking up into the atmosphere that there were changes in chemicals, specifically the ozone layer, which is necessary for life on Earth. So the ozone layer really protects us from harmful.
It's like this thin little veil that
Yes,
keeps
it's
certain
very,
kinds of-
very thin. If you brought all the ozone down to the surface, the layer would be this big.
Yeah.
But that protects all life on Earth and has allowed life to evolve to the point that it did. If the ozone layer was there, we never would have had life as we know it.
No.
And so it's very necessary. And these fires caused changes. And so we actually saw a reduction in ozone for a few months over Australia.
Okay, that's what I wondered, whether the fires on the ground are in Australia. Does the cloud and the particulate matter and the chemistry of the cloud, does it stay put over that spot of the Earth, or does it kind of scrape along?
It does move, but it didn't spread all over the globe.
No.
So it stayed in the southern hemisphere and primarily around the site of injection into the stratosphere. And so I said we saw that reduction in ozone, and there's been a lot of research trying to look into, well, what caused that reduction? Because the injection of these clouds, and they were pretty hot because they're coming from fires and smoke. It's to change the temperature of the stratosphere, and a lot of the chemical reactions that form ozone, or just the ones that deplete ozone, because there's this balance,
Right.
are very temperature dependent. So if you change the temperature, you're going to change rates of reactions and what's happening. And then it was injecting new particles that aren't normally in the stratosphere.
Yeah.
And so there were what we call dynamical changes, so changes just how the winds are moving in the stratosphere, as well as chemical changes. And then this was affecting ozone.
Yeah.
Now, what we don't know yet is exactly what portion of dynamics and chemicals caused this change. So we saw about 100, we use the units Dobson unit change in ozone,
Yes,
just a
after
measure.
Mr. Dobson.
Exactly.
Yes.
And normally over that area of the globe, there's a couple hundred Dobson units. So seeing 100 Dobson unit drop is pretty rare for that area. And so it was something that was noticeable. And there's still research going on right now to try to figure out, exactly what was happening and what portion of the decrease was due to dynamics, what portion was due to chemical changes. And what was very interesting is that the fires brought these particles called aerosols into the stratosphere.
We know about aerosols because that's the way COVID viruses.
Exactly,
Travel
yep. So the
from-
suspended liquid particles in the air. And there can normally be aerosols in the stratosphere due to volcanic eruptions.
Okay,
They put something called,
really powerful.
right, and they put something called sulfate aerosols into the stratosphere. And the presence of sulfate aerosols leads to ozone depletion. But the types of aerosols that were present to the fires were not sulfate based. They were organic based. And so the chemistry that's occurring right now, our best evidence shows it's not the same that normally occurs on sulfate aerosols. And so the mechanisms through how ozone is depleted is something we don't necessarily know yet, because we haven't really seen organic aerosols go into the stratosphere, and no one's really studied them to figure out, how is ozone depleted with those types of aerosols.
And organic aerosols have carbon in them and oxygen in
and
them.
Oxygen, and yes. And so it's different chemistry that is happening. And we've seen this through satellite measurements showing us the chemicals that are present. And we weren't seeing what we expected if there had been sulfate aerosols. So we're like, okay, that means something's different, and then found out through more measurements that the types of aerosols are different. So this is an active area of research right now, trying to figure out why there were organic aerosols. So is there something special about eucalyptus trees, which is what we're burning?
Right, along
In
with all the
Australia?
little koala.
Yes. And does that create certain types of aerosols? And what's the chemistry that's happening? And so this is what researchers are looking at right now to try to figure out, just what happened, so we know. And then for the future, if there is another big wildfire in Australia or somewhere else, what could we expect to see? So we have a better handle of what might happen in the future.
And that's how you establish different baselines and different measurements and parameters, and then you can tell what's different this time or what's the same or
Exactly.
something like that. And you mentioned observation both from satellites and from the ground. I know that ozone was sort of first discovered and figured out through ground observations, right? There were no satellites at that moment. Maybe balloons, but maybe not.
Yeah, they had balloon-borne instruments as well at the time. But satellites we really didn't start to have satellite measurements till 1979.
Yeah, and how do the satellites, they have sensors on them, or is it a visual observation? Or?
So they have sensors, and so it depends kind of what you're measuring, how the measurements take place. So you can kind of look at how light is reflected in the atmosphere to get a sense of certain chemicals. Look at how sunlight is absorbed. You can also send lasers from a satellite down and see, does it penetrate to the surface, or how much of that laser beam penetrates, and that tells you what could be in the path that could be affecting it. And so there's many different ways that a satellite can take measurements of species in the atmosphere.
So it can shine its own little light through
So
there.
it can
It's not
shine-
simply measuring the impact of sunlight and solar radiation.
And so it's depending on where you are on the globe and what you're looking at, you have these different measurements. And if you're trying to look at something at night, you obviously can't use a method that needs sunlight. And so we do have ways to take measurements at night so that we can see what's in the atmosphere.
So when you were looking up at this enormous, unusual high cloud, were you in Australia as you were doing it, or were you accessing data from observation points down under? Or?
Right. I was not in Australia, and so I was looking at data that had been collected, and I was just at the University of Maryland. So a lot of research I do is on the computer, and so I take data that's been collected by others, and then I take that data and I look at it and analyze it to figure out what's going on. And so I was not there during data collection. But I use what other scientists have found
Yeah, and that makes sense. And when we're talking about the atmosphere, we're talking about tiny little fractions, tiny little proportions
Yes.
with huge consequences, right? And I think that's something that viewers need to wrap their heads around. We're talking about parts per million.
Yes.
And just a slight 1/10 of a part per million change can alter the amount of radiation hitting the Earth's surface.
Yes, and that, it took me a while to sort of understand that when I was really first getting into the field and learning all this information, is with the ozone layer as well as with climate change, it's just very small concentrations of gases, and you change those a little bit and you have worldwide impacts.
Yeah.
And it is a little hard to wrap our head around, just being like, how can something that really isn't present that much have such a big impact? But it's because of what they do, and that.
Also, I think sitting down here on Earth and looking up at big fluffy clouds, we imagine that the sky goes on for a long way and that the atmosphere is really thick, but it's not. The stratosphere is as close as Pottstown.
Yeah, it's,
right?
You could, I forget who said it, but if you got in your car and you drove straight up, you would be in space in about a couple hours.
Yeah.
It's really, the atmosphere is very, very thin, but yet it's vital for life on Earth.
This wouldn't be
and,
us. Yeah.
Right, protects us from, solar radiation that could harm us, from, comets, meteorites coming from space. They burn up in parts of the atmosphere, and it's a very, very important part of Earth. But it's hard to understand because you can't do experiments on it. So when a lot of people think of chemistry, they think of us, in a lab, at a bench, putting stuff in beakers and mixing things, which is a big part of chemistry. But there's also the field-based.
Yeah.
And the environment is something that you really can't do an experiment on because it's so big, it's hard to get to certain places. And so you have to use models. You have to take measurements and infer what could be happening. And so it's just a different form or different type of science than is most people normally think of, but it's very important because if something drastic happened to the atmosphere, that affects us.
Yeah, I guess you wouldn't want to do an experiment like, I don't know, filling hairspray cans with all sorts of propellants and spraying those around for 30 years. And
So we already did that one.
Oh, we did that one, yeah. That was a field experiment that was performed by humankind in sort of a misguided attempt to keep our hair in place. Wow. The wildfires, are those a naturally occurring phenomenon, or is the intensity of those, is that an effect of climate change, do you think?
Both.
Yeah.
So wildfires are natural. We wouldn't call them wildfires if they were just set by humans. And they happen because of lightning strikes or something else causes something to start to burn. And then as areas are dry, there's drought, then there's a lot of fuel around.
Yeah.
And so then they can burn fast and very intensely. And that's what we're starting to see. So Australia wasn't the only example. There's been a lot of wildfires out west here in the United States, California, Colorado, Arizona, Washington. We hear every summer, every fall about how there's these just devastating fires. And we expect there to be more increases in wildfires and the intensity of wildfires as areas become more dry due to climate change.
And that intensity must be the really scary part of them, because that's what generates all that energy that might rise up to the stratosphere.
And so as a society, we need to really start investing in just fire management in these areas that are prone to wildfires, because we're not going to be able to stop wildfires, but we can try to prevent them becoming very severe or intense by, clearing underbrush that's just dead.
Yeah.
Or making sure that we're not building homes and towns in areas that are, normally wilderness, because wilderness areas are...
It might be scenic, but it's not supposed to be habited by human beings.
Exactly. And so areas that do have a lot of fuel, the wildfire doesn't care if there's a town in its path. It's going to burn whatever's there. And so to keep humans safe, we need to make sure we're being smart with how we're managing areas and where we're building and things like that.
Yeah.
And so these are things that, places that have wildfires, the authorities are already thinking about this.
They have to be.
And so it's just something out here in Pennsylvania we probably don't normally think about because we don't normally have wildfires and we're not projected to. So it's not all, we're not all of a sudden going to start having it here.
So that helps us. Yeah.
But it's just, I would expect us to just see more and more on the news that there's these bigger and bigger fires.
Yeah.
And that they could start to be having an effect on not just what's happening on the surface with potential air quality and things like that, but in the second layer of the atmosphere and the stratosphere,
Right.
we could see effects too.
So global effects, not just local effects.
Exactly.
Yeah, yeah. Well, this is fascinating. I bet your classes are fascinating as well. What are you teaching this semester?
I think they're fascinating. I hope the students do too. So this semester I'm teaching an Introduction to Global Climate Change course.
Oh, wow.
And then I'm also teaching an environmental chemistry course. And so in that class, I've actually just finished the module on the stratosphere. And my students and I, we talked about how wildfires can affect ozone. And in the global climate course, we do just a survey of what's part of the climate system and what's happened in the past, what's happening now, what's happening in the future, and then what are strategies that we can use to deal with the effects that we're seeing, and how can individuals make a difference.
And are most of your students in that class chemistry majors? Are they science majors?
In the climate course, I have students from all majors. This semester, I actually have a lot of business.
Wow, is this a
majors.
connections course?
It is. So it
And I assume a
satisfies-
global connections
It
course.
is.
Yes.
So it satisfies a gen ed requirement for the students, and then it's also part of the new sustainable business minor. And so it
great.
helps satisfy a requirement for that. And so it's really nice having students from different majors and not just chemistry or science majors, because the students can draw on things that they've learned in their classes that they've taken for their major and how it relates to this class. So right now the course is pretty science heavy because we're going into the technical aspects, how does the ocean affect climate and things like that. But once we start getting into what are solutions, what are ways we can deal with this, that's where students, especially in the humanities or in business, things like that, they can really bring their expertise to the class and help share their ideas or what they've talked about. And it really helps enrich the course.
That's great. That's great. I teach a number of gen ed courses. All my courses, I think, are gen ed. And I always invite people with different majors to bring in their expertise, their methodologies, their strategies, because it all enriches that mix and
Exactly.
that conversation as well. Have you mentored individual students in their research yet, or is that
I am
something in the
starting this
works?
semester.
Okay.
So I have 2 students who are doing independent study projects with me. And so a lot of the work, I believe I mentioned previously, I do on the computer. So
Yeah.
it's through programming. And so I'm teaching 2 students right now how to use a programming language called Python. And then we're going to analyze some climate data, and each student's come up with their own question that they want to try to answer using the data. And so they're learning Python to be able to look at the data and analyze it to answer their question.
How great.
And so that's been really exciting so far, and I've been really enjoying it. And so I look forward to working with them through the rest of the semester on this project.
Again, it's what comes around, goes around, comes around. So the fact that you were mentored as an undergraduate allows you to return that favor,
Exactly, yep.
and you know what it's going to mean to them as they get more and more into their projects and their
Yes.
curiosities as well. This is great. I have to say too that you've landed in a lovely department. I have so many friends in the chemistry department with a wonderful range of interests in the sciences, but
Yes.
in other ways as well. There's a chemistry of food course
Yes.
happening now. There's a course on chemistry and the arts
Yes.
as well. So yeah, it's a wonderful group of colleagues that you're.
Yeah, I've been really
with.
enjoying it so far, and everyone's been very supportive and very nice. And so I really enjoy my department, and I really like my colleagues.
I am
It's
so
been great.
glad. I'm so glad. Well, Laura, thank you so much for sharing this deep insight into atmospheric science and your own work. And congratulations on the article in Science Magazine. I think you have to subscribe in order to read the whole thing, right? I've read the
Yes.
abstract online.
Yes, though I do have a copy, so if
Okay.
you would like it, or
Well, I think I probably
any
better
of our
now.
viewers would like it, then I'm happy to share it.
Okay, great. Thank you. And thank you as well for joining us today on the Albright Scholar. We'll be back again in another month's time with another edition of the Albright Scholar. So long.